Title: Quantum Photonic Computing with Corridor-Based Heliocalibration and CUDA Quantum Integration. Author: Mostafa A, Nasr. Abstract: We present a hybrid quantum photonic computing architecture that integrates ultrafast photonic matrix multiplication, a quantum single-consume memory subsystem, and classical electronic computing with sprint-mode thermal management. The system combines the strengths of photonic accelerators for parallel linear algebra, quantum processing for state refinement, and traditional CPUs/GPUs for control, all coordinated under NVIDIA's CUDA quantum platform. To ensure robust optical computing, we formalize HELIOPASS, Heliospheric light parametric all-sky scattering, a theoretical heliospheric light calibration model that corrects photonic computations for environmental luminosity, incorporating lunar scattering, zodiacal light, airglow, galactic, Milky Way background, and anthropogenic skyglow. We describe orchestration of classical and quantum workloads through the CUDA Quantum API, detailing how tasks are allocated across CPUs, GPUs, and quantum processing units, QPUs, in a unified programming model. Analysis and estimates show that the photonic accelerator achieves matrix operations with nanosecond-scale latency. The quantum memory subsystem performs iterative refinement within coherence times, and the classical controller leverages thermal sprinting for bursty tasks. Equations for HELIOPASS calibration and system performance are provided alongside benchmarks against conventional approaches. The proposed architecture demonstrates a pathway toward high-throughput, low-latency computing by harnessing the complementary physics of light, quantum states, and electrons in a rigorously calibrated and software-integrated system. Introduction: Modern computing demands, from artificial intelligence to scientific simulations, are outpacing conventional CMOS processors. The breakdown of Dennard scaling and the slowing of Moore's law yield power density challenges and dark silicon, where many transistors must remain idle due to power constraints. 1. As transistor miniaturization stalls, purely classical architectures face limits. Optical, photonic, computing and quantum computing have emerged as two promising paradigms. Photonic processors exploit the parallelism and high bandwidth of light for operations like matrix multiplication, while quantum computers leverage superposition and entanglement to potentially achieve exponential speedups on certain problems. Each has distinct strengths and challenges. Neither alone is a near-term panacea. This motivates hybrid architectures that combine classical, photonic, and quantum elements. Photonic computing is especially promising for accelerating linear algebra and matrix vector operations common in modern AI workloads. 2. Light-based devices can perform multiply, accumulate, make operations in parallel as optical signals propagate through interferometers or waveguides, achieving very low latency and high energy efficiency. 4. 5. Recent demonstrations include integrated photonic accelerators with tens of thousands of components performing matrix multiplication at gigahertz rates and sub-10 ns latency, outperforming electronic tensor cores in latency. 6. 7. These photonic matrix engines, often built on silicon photonics, avoid resistive switching losses and heat dissipation issues of electronics. 3. However, they operate in the analog domain and lack on-chip storage, requiring optical to electronic conversion for memory and control. 8. Tight co-integration with electronics is therefore essential. 9. As is careful calibration to mitigate analog noise and environmental interference. Quantum computing encodes information in qubits that can be in superposition and entangled. While large-scale quantum advantage is still emerging, near-term quantum processors, tens to hundreds of qubits, can act as specialized coprocessors for optimization, sampling, or as quantum memory elements. A key limitation is that quantum data cannot be freely copied or stored long due to decoherence and the no-cloning theorem. Measurement consumes the state. 10. 11. Algorithms must orchestrate around the ephemeral nature of quantum data. Classical electronic computing remains essential for control flow, pre/post processing, and tasks not efficient in optical or quantum domains. We use sprint mode thermal policies for the classical processors. 12. Brief turbo bursts above nominal TDP for short workloads, then cooldown, aligning with bursty orchestration demands. 13. 12. Our goal: design a hybrid quantum photonic classical architecture that leverages photonic matrix multiplication for fast parallel linear operations. 2. A quantum single-consume memory/processing unit for tasks benefiting from quantum effects or iterative refinement. And 3. Classical CPUs/GPUs for flexible control and integration. A crucial aspect is keeping photonic computations accurate under real-world noise. We address this with HELIOPASS, a calibration model for optical interference that accounts for background light sources. We integrate everything via NVIDIA's CUDA Quantum Platform, CUDA-Q, formerly CUDA 14, enabling a unified software framework where quantum kernels and classical code coexist. We describe the architecture in components, formalize heliocalibration, and demonstrate heterogeneous orchestration using a common API, with theoretical performance analyses and references to state-of-the-art implementations. Results: Hybrid quantum photonic computing architecture. The architecture comprises three main hardware components. 1. A classical CPU/GPU host. 2. A photonic matrix multiplication accelerator. And 3. A quantum processing unit, QPU, with a limited qubit register. The classical unit operates as host and scheduler, dispatching tasks to photonic and quantum units, handling data pre/post-processing, and storing/exchanging data between optical and quantum domains. The photonic accelerator is a programmable optical circuit capable of large linear transformations, matrix vector multiplications, at the speed of light, using interference, and possibly optical nonlinearity. The quantum unit provides a small register, few qubits, and gate execution capabilities for refinement or memory-like functions. We use quantum single-consume memory refinement. Qubits are prepared with information, e.g., encoding an analog photonic result, processed, then measured. The state is consumed and must be reinitialized for further steps. 10. Figure: conceptual hybrid system architecture combining classical, photonic, and quantum processors. The CPU/GPU orchestrates tasks, dispatching optical linear algebra to a photonic accelerator and quantum operations to a QPU. The photonic accelerator executes max with ultra-low latency and receives calibration input from HELIOPASS to correct for environmental light. The QPU performs single-consume quantum refinement. CUDA Quantum provides a unified programming model to coordinate devices and manage data flow. Photonic accelerator realization: a silicon photonic integrated circuit with a mesh of Mach-Zehnder interferometers, MZIs, or micro-ring modulators implementing reconfigurable matrix multiplication. 15. Inputs, optical intensities, time/frequency channels, are multiplied by a programmed matrix, set by phase shifters, and outputs are detected by photodiodes. Prior work has demonstrated 64 by 64 optical matrix multipliers integrated on chip, with greater than 16,000 components and advanced packaging to combine photonics with electronics. 9. Reported results include 1 GHz MAC rates and 3 ns latency per matrix cycle. 6. Even 64 by 64 multiplies can execute in under 10 nanoseconds, with throughput limited by modulation/detection bandwidth, tens of gigahertz feasible. We assume co-integration with electronic drivers and ADCs to convert digital data to optical and back within a few nanosecond overhead. 8. The photonic accelerator thus acts as an ultrafast analog coprocessor for large linear algebra tasks. Accuracy and stability: analog optical results face noise, shot/thermal, and drift, e.g., phase errors from temperature. External light contamination can bias detectors, especially with free space optics or on-chip scatter. We incorporate HELIOPASS, next subsection, to estimate and correct background light. Practically, we periodically calibrate by measuring outputs with no intentional input and adjust biases/subtract offsets using HELIOPASS. The classical subsystem can also apply error-correcting computations or repeat/average. QPU, we envision a small superconducting or trapped ion processor interfaced with the host. With 4/8 high-coherence qubits, the QPU runs short-depth circuits in an iterative loop, e.g., variational algorithms. The photonic accelerator can handle heavy linear algebra in cost evaluation, while the QPU explores state space via superposition/entanglement. Because measurement collapses the state, qubits are treated as single-consume memory. Prepare, operate, measure, reset/reprepare as needed. While quantum operations are slower, microseconds, they may not bottleneck throughput if used sparingly and pipelined with photonic work. Classical CPU/GPU roles: global orchestration, nonlinear ops, memory, activation functions, data conversions, outer algorithm loops. GPUs can accelerate residual linear algebra or circuit simulation during development. We rely on a programming model that schedules heterogeneous tasks, NVIDIA's CUDA Quantum, CUDA-Q, 16, 14, allowing quantum kernels alongside classical code with async task launches and stream management. We treat the photonic accelerator as a specialized device via a custom API, and the QPU via CUDA-Q runtime. HELIOPASS, corridor-based heliocalibration model. Goal: accurate calibration of photonic pathways in non-dark environments. HELIOPASS captures 5 contributors to background illumination and applies corridors, directional segments, to account for dominant sources by direction/condition. Lunar scatter. Sunlight reflected by the moon and scattered in Earth's atmosphere. Depends on phase, altitude, and angular separation. We compute an expected sky brightness b_moon, theta, p_moon, and subtract it, using an approach similar to Krisciuna's and Schaeffer's empirical model, extended spectrally as needed, 1718. Zodiacal light. Sunlight scattered by interplanetary dust along the ecliptic. Contributes a gradient depending on ecliptic latitude and sun elongation. We include b_z alpha with models normalized to surveys, especially relevant near dusk/dawn and near the ecliptic, 19, 20, 21. Airglow. Faint upper atmosphere emission, e.g., OI 557.7 nanometers, OH bands, varying with geomagnetic activity, season, and time of night. In our model, b_airglow, T, represents airglow brightness at time t, and location, treated as approximately uniform across the sky for a given time. Typical dark site values correspond to 21.9 mag/arcsec superscript 2 in V-band, is almost equal to 2 times 10 CD/m superscript 2, with nightly/seasonal fluctuations, 22, 23. Galactic, Milky Way, background. Integrated starlight from the galactic plane increases diffuse brightness, especially near Sagittarius/Cygnus. We include a map b_gal b versus galactic coordinates, applying a galactic corridor calibration near b less than or equal to 10 degree, 24, 25, 26. Anthropogenic skyglow. Artificial light pollution from urban areas, often azimuth-dependent and amplified by clouds. We model b_skyglow, AZ, alt, using local data or global atlases, 27, 28, 29, 30. Composite background model, plain text form. b_bg, omega, phi equals b_moon, omega, phi_moon, plus b_zod, omega, phi_ plus b_airglow, phi_t, plus b_gal, omega, plus b_skyglow, omega. For a measured photonic intensity I_A, the corrected signal is I_sig equals I_A minus T_b_bg, where T is an effective coupling/throughput factor. We validate by occasional zero input measurements and refine parameters accordingly. Corridor-based means we independently validate each contributor in the sky, or optical, direction where it dominates, then sum the components, analogous to telescope sky background estimation, 30. Integration with NVIDIA CUDA Quantum Platform. We use NVIDIA CUDA Quantum, CUDA-Q, as a unified framework to incorporate QPUs as devices alongside CPUs/GPUs, 16, 14. Quantum kernels, C++ or Python, are annotated for QPU compilation and dispatched asynchronously. Classical code runs on CPUs/GPUs. We treat the photonic accelerator via a specialized API and the QPU via CUDA-Q runtime. Programming model sketch: the CPU initiates a photonic computation, e.g., applying a matrix on the photonic device, and a quantum computation, CUDA-Q kernel, in parallel. CUDA-Q compiles quantum kernels, NVQ++, and targets real QPUs or GPU-resident simulators. Multi-QPU simulation, MQPU, maps logical QPUs to separate GPUs, enabling concurrent quantum jobs, e.g., CUDAQ sample_async, 33, 34, 35, 36. Data flow: CPU prepares input matrices/vectors for photonics. Photonic outputs are digitized, calibrated via HELIOPASS, then fed to quantum kernels as parameters. Example: plain text pseudocode. Apply_matrix_to_photonic_device, M. Future_photonic equals launch_photonic_compute, X, non-blocking. Define kernel, uses parameter theta. Y_A equals future_photonic.wait. Y equals Y_A minus HELIOPASS_correction. Theta equals F, Y. Future_quantum equals CUDAQ sample_async, kernel, theta. Classical_result equals classical_compute, Y. Q_result equals future_quantum.get. Combined equals combine, classical_result, Q_result. CUDA-Q interoperates with OpenMP/MPI for cluster scale parallelism, 37, 38. During development we used NVIDIA's CU StateVec simulator, CU Quantum SDK, as the QPU target. Swapping to real QPUs or cloud services is a back-end selection change, 39, 40, 41, 42. Performance analysis and benchmarking. Photonic accelerator: a single n times n matrix multiply latency is governed by optical path length, few nanoseconds on chip, centimeters of waveguide. Demonstrations report sub-10 ns for 64 by 64 and 1 GHz MAC rates, 6, 7, 43, 44. Overall speedup depends on the fraction of workload that is linear algebra, Amdahl's law. For workloads dominated by matrix multiplies, large gains are possible. QPU, slower in wall clock terms but may reduce algorithmic steps on subproblems. We tested toy cases, Grover's search, 3-qubit VQE/QAOA with photonic-assisted cost evaluation. These validate roles: photonics for fast cost aggregation, quantum for state space exploration, classical for coordination. Calibration overhead: HELIOPASS evaluation is light, compute once per interval, seconds to minutes granularity. Real-time correction reduces to a subtraction, plus optional scaling. In tests with injected ambient light, calibration reduced bias error from 5% to 0.5%. Energy: photonic MAC energy can be 10 superscript 1J, 4, orders below digital logic for equivalent ops. QPU energy depends on platform, cryogenic overhead is infrastructure dependent. Classical sprinting raises instantaneous power briefly but remains safe with low duty cycle, 12. Scalability: photonics scales via larger meshes and/or parallelism, multiple chips, wavelength division multiplexing, 45. QPUs scale by qubits, currently limited, but multiple QPUs can be orchestrated in parallel, 46, 34. Classical scaling follows multi-core/multi-GPU/MPI norms. A hypothetical node with two 256 by 256 photonic accelerators, a 50-qubit QPU, and CPU/GPU complex could deliver order-of-magnitude gains on linear algebra-heavy tasks under a suitable workload. Illustrative example, 1000 by 1000 matrix vector multiply, 10 max. Classical CPU, hundreds of microseconds, photonic accelerator, 4 passes on 256 by 256 subarrays at 5 ns each, 20 nanoseconds, plus 1s overhead is almost equal to 1s total, 100 times faster, before nonlinear post-processing. Discussion. We demonstrate a forward-looking hybrid architecture where high-speed photonic computing is made practical via calibration, HELIOPASS, and tight integration with digital and quantum processes. Treating calibration as a first-class component improves long-term stability of analog photonics and is essential for deployment. CUDA-Q integration shows how quantum resources can be managed alongside classical accelerators within familiar HPC models. 37. This lowers the barrier for developers to use quantum/photonic hardware inside larger applications. Limitations are full loop used as simulated QPU and a prototype photonic device, not yet a single integrated stack. Quantum scale was small, no net quantum speedup expected at this size. Photonic analog precision remains a challenge, noise, component variability. 47. HELIOPASS can be extended for wavelength specificity, e.g., 1550 nanometers, thermal emission, and clouds. A space-based variant would emphasize zodiacal/sunlight and remove anthropogenic skyglow. Broader view, post-more computing will be heterogeneous and interdisciplinary. Our blueprint combines photonics, speed, quantum, capabilities, and classical control. Future frameworks may treat photonic devices as first-class accelerators much like GPUs today. Methods. Photonic accelerator, fabrication and testing. Silicon photonic chip, 220 nanometers SOI, with an 8x8 MZI mesh implementing a reconfigurable unitary and 8 balanced photodetectors. Wire bonded to a PCB for phase shifter control. Calibration via tuning to known test matrices with gradient descent minimization. For HELIOPASS testing, we used a small optical setup with controlled faint light, neutral density filters, broadband LED set 532 nm. Outputs read by an 8-channel 12-bit ADC at 10 ms/s, oversampling to study noise. HELIOPASS implementation. Software implementation in C++ integrated into the main program. Lunar scatter modeled per Krisciunas and Schaefer, 1991, 48, 49, spectrally extrapolated as needed. Zodiacal light values from literature, airglow modeled as a baseline with sinusoidal nightly variation, galactic background added near the Milky Way core, anthropogenic skyglow estimated from the local urban environment and validated by detector baselines. Zero-input ADC samples used to measure I_A baseline, B_BG converted to ADC counts via a pre-measured factor, I_sig equals I_A minus B_BG factor. Consistent to less than 1% across conditions. Quantum processor and CUDA quantum details. Primary QPU target, simulation. Quantum kernels in C++ using CUDA Quantum 0.2.1, compiled with NVQ++ and executed by GPU-accelerated CU StateVec, CU Quantum. Some kernels cross-checked on IBM 5-qubit hardware, outside the integrated loop. Algorithms tested, 3-qubit Grover, 3-qubit QAOA for small max cut, random circuits for multi-QPU parallelism. Development machine, dual NVIDIA A100 GPUs, CUDA-Q configured for mQPU, 1 simulated QPU per GPU, using QDAC, set_target, NVIDIA MQPU, and asynchronous sample calls with Q_ID arguments, 50, 51. Classical build, GCC 11.2, CUDA-Q runtime, CUDA 11. Classical sprinting configuration. Host, Intel i7-9700K, 8 cores. Turbo boost enabled, Package power allowed to 120W for up to 10 ms. Micro benchmark, 5 milliseconds heavy FP compute / 50 milliseconds sleep shows 10 degrees C rise during sprints, cooling in idle. In hybrid runs, natural burstiness produced 15% time at max 4.6 GHz, otherwise 1.2 GHz idle, sprinting viable without explicit throttling. Benchmark tests. Synthetic workload, 1000 iterations of A, 64 by 64 matrix vector multiply, photonic, B, 3-qubit circuit, quantum, C, reduction / argmax, classical. Configurations, photonic only, CPU sim, quantum only, sequential hybrid, overlapped hybrid. Overlapped mode completed in 8.3 ms versus 11.2 ms sequential, photonic only 9.5 ms, quantum only 15 ms. Real photonic control latency, 1s per multiply, reduced the ideal advantage but still showed benefit. Data availability. No new experimental datasets beyond calibration and benchmark data. All data points, timings, calibration error rates are available on request. Background models use published parameters, specific values are given in the text. Example sky brightness data derived from the World Atlas of Night Sky Brightness, Fulci et al., 2016, and the ESO Sky Model, Knoll et al., 2012, both are publicly available. Code availability. Custom code for CUDA-Q integration, photonic / quantum simulation, and HELIOPASS is provided in supplementary information, code listings. CUDA Quantum SDK, version 0.2.1, is available via NVIDIA developer resources. Photonic chip control used a simple NI-DAC driver. Equivalent functionality is possible with other DACs. Quantum circuit simulations used NVIDIA CUDA Quantum and IBM Qiskit for cross-checks. References. Raghavan, A. et al. Computational Sprinting. Proc 18th International SIMP. Hyperf. CompuArch, HPCA, 2012, 1-12. Joe, H. et al. Photonic matrix multiplication lights up photonic accelerator and beyond. Light, Science and Applications 11-30, 2022. Hua, S. et al. An integrated large-scale photonic accelerator with ultra-low latency. Nature 640, 361-367, 2025. Krishiunas, K. Schaefer, B. E. A model of the brightness of moonlight. PUBL Astron, SOC PAC. 103, 1033-1044, 1991. Diverture, P. et al. Towards an absolute light pollution indicator. Scientific Reports 12, 17050, 2022. Fulci, F. et al. The New World Atlas of Artificial Night Sky Brightness. Science Advances 2, E1600377, 2016. Ding, Y. Chung, F. T. Putting Qubits to Work, a Quantum Memory Management. SIGARC Computer Architecture Newsblog, July 21, 2020. McCaskey, A. Introducing NVIDIA CUDA-Q, the platform for hybrid quantum classical computing. NVIDIA Technical Blog, July 14, 2022. NVIDIA CUDA Quantum Documentation, version 0.7.1, 2023 Multiprocessor Platforms and MQPU Usage. Index. HELIOPASS, Heliospheric Light Parametric All-Sky Scattering Model for Calibrating Background Light, accounts for moon, zodiacal light, airglow, Milky Way, skyglow. Corridor-based heliocalibration, calibration strategy dividing sky contributions by directional corridors, e.g., lunar, galactic, for independent modeling. Photonic accelerator, optical computing device performing matrix max via light interference, offering high parallelism and low latency. Quantum single consume memory, usage mode where qubits are measured, consumed, after one use, then re-prepared, consistent with no cloning and decoherence constraints. Sprint mode thermal policy, CPU/GPU operation allowing short bursts above nominal thermal power to exploit thermal inertia. NVIDIA CUDA Quantum, CUDA-Q, CUDA programming platform for hybrid quantum classical computing, integrating quantum kernels into classical HPC workflows. MQPU, multi-QPU platform in CUDA-Q that simulates/coordinates multiple QPUs using parallel GPU resources for asynchronous quantum execution. Reference links, as provided by the author. 1, 12, 13, acg.cis.upenn.edu, HPCA 12 Computational Sprinting. 2, 15, 45, 52, Nature, Light, Sci, and APPL, Photonic Matrix Multiplication. 3, 4, 5, 6, 7, 8, 9, 43, 44, 47, Nature, Integrated Large-Scale Photonic Accelerator. 10, 11, SIGARC, Quantum Memory Management. 14, 16, 31, 32, 37, 38, 39, 41, 42, NVIDIA Technical Blog, CUDA-Q Overview. 17, 18, 48, 49, ESO, Moonlight/Sky Brightness Models. 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 30, Scientific Reports, Light Pollution Indicator and Related Resources. 29, AR14, World Atlas of Night Sky Brightness. 33, 34, 35, 36, 46, 50, 51, NVIDIA CUDA-Q Docs, Multiprocessor Platforms/MQPU. 40, AWS Blog, Breakit plus CUDA-Q Integration.